But today there's going to be a reception from 6 to 8 for all of you guys that's being set up there. So there is less space there than usual. And there are also fewer problems than usual because most of the lecturers haven't gotten around to writing their problems yet. Instead we're going to ask you guys to either use this space for problem solving in the afternoon or the classrooms that are listed on the website down in Lorentzian. So on the following days of the school, you can use the 4th floor. And the other comment is that we have this room for the day, but the area around the patio where you guys were getting drinks and snacks is not actually ours during the day. So in the afternoons, please don't hang out there. That's not our space to use. So that's it. Those are the annoying organizational announcements. So now I'll turn it over to Dalimil for some physics.
Thanks a lot, David, and thanks also to all the organizers for bringing us all here to what promises to be a very, very exciting school, and especially to this lecture room which has some amazing history and luckily also air conditioning. So I'm definitely not as David said, I'll give you an introduction to the conformal bootstrap. And I have to say that I'm definitely not the first person in the history of conformal bootstrap that has this task. And luckily for us, the previous people who had this task left behind some wonderful set of resources. So let me give you references to those. I can highly recommend lecture notes by Slava Rychkov, given at EPFL. So you can find them under the name EPFL lectures on conformal field theory. And also great notes by David Simons-Duffin from TASI. Both these sets of lecture notes cover the basics of CFTs in slightly more depth and rigor than what I'm going to have time for. You can find both of these on the archive. And also, if you're more or less a newcomer to the world of the conformal bootstrap, then you can also watch Chris's lectures from last year at the Bootstrap School in Brazil. Chris Beam Bootstrap School. And these are on YouTube. And I can also highly recommend to solve the problem set that he set at this school. So if you want to make sure that you really understand all the Bootstrap basics, the best way to verify that you understand it is to go through Chris's wonderful set of problems. So because there are all these previous great resources about conformal bootstrap, and this is not the first Bootstrap school, I decided that the path through the introduction in my lectures is going to be a little bit quicker than last year. And one thing which especially guided me in deciding what I'm going to talk about is to focus a little bit more on the things which confused me when I was a graduate student, when I was learning about this topic, and actually in some cases which confused me up until I decided to prepare these lectures. And in some cases I still feel like I don't really understand some of the things, but hopefully by the end of this school the overall level of confusion is going to go down. But without further ado, let me give you the outline of my lectures. The first lecture is going to be still pretty basic, if a little bit quick. So I'm going to discuss the CFT basics or CFT axioms that we use in the conformal bootstrap. Then in lecture 2, everything is going to be set up to discuss an absolutely remarkable equation that we all love in the Bootstrap community, namely the crossing equation. So I'm going to say as many interesting things about the crossing equation as possible. And then depending on the time, how much overflow material there is going to be, but if there is time, I'll try to talk about some recent developments in trying to understand some analytic bounds following from the crossing equation in some simple situations. Okay. that's the outline. And before going into any technical details, let me talk a bit for why we should care about conformal field theories and the conformal bootstrap. So I'm sure all of you here know that conformal field theory is a quantum field theory with a conformal symmetry. But why are they interesting? Well, I guess the short answer to that is that conformal field theories are absolutely ubiquitous in the world of quantum field theory, and on top of that, they are much more tractable than ordinary quantum field theories without conformal symmetry. Probably the most important situation where the language of conformal field theories is useful is the fact that they organize the space of quantum field theories. So you can think of a typical RG flow, but perhaps not about every RG flow or every quantum field theory, but about a typical one. You can think of as a flow from some UV CFT to some IR CFT. So you should think of the space of RG flows as having these fixed points, which are the CFTs, and you can flow in various ways between them. So in this way, they organize the space of quantum field theories. And they are much more tractable than a general quantum field theory. And now, importantly, if you know everything about the conformal field theory, and I'm going to say what this word "everything" means later, you in principle also know everything about the RG flows. Now, this is an important in principle. Like it's not. It doesn't mean that if you solve a conformal field theory exactly, then you have automatically solved all RG flows that come from it. But it's definitely a big progress to understanding also a general quantum field theory. Now the second situation where conformal field theories are absolutely essential is when you study some quantum system put inside ADS. So let's imagine that we have ADS space, and there is some quantum, not necessarily gravitational, but some quantum system inside ADS. Now, the claim is that such a system is very generally described by a conformal field theory living on the boundary. And an important special case of this setup is when there is actually gravity inside ADS, which means that which translates in this dictionary in the locality of the conformal field theory. And I'm going to explain later what locality exactly means. So if we have gravity in the bulk, that's the same thing as having a local CFT on the boundary. But as I said before, the setup is more general, and you can consider putting non-gravitational quantum field theories in ADS, and that it is still described by conformal invariant theory on the boundary. And I mean the essential importance of this setup is that it is really the only non-perturbative description that we have of quantum gravity. And finally, maybe a point which seems to be losing importance with time, but I think it's still a very important one, and it should be revisited, is the fact that the worldsheet string theory is a CFT. Worldsheet string theory. So by understanding the landscape of two-dimensional conformal field theories with a specific central charge, you're also understanding the landscape of string theory vacua. Are there any questions about this basic setup or basic motivation? So there are clearly many different ways to define conformal field theories. You can start with a Lagrangian, quantize it, flow to the IR, and find some conformal field theory in the field theory there. Or you can start with some lattice model, go to the criticality, find a CFT there. You can use string theory constructions, but somehow in many of these situations, there are some hard problems that you can ask about a CFT, which the description just is not capable of solving, or which are very hard to answer in the description. Like, for example, you may want to answer the question, what is the landscape of all quantum gravity theories inside ADS4? And none of the particular definitions of the CFTs gives you an answer to that. Or you may ask, what are the critical exponents of the three-dimensional Ising model at criticality, and okay, you can maybe do Monte Carlo, or you can try to compute the epsilon expansion, but you're going to have to work very hard, and in many cases, such questions are really impossible to answer, which is where the conformal bootstrap comes in. Okay, the other thing I should also say is that in many cases there could be completely different definitions, maybe path integral or some lattice model or even a string theory construction that actually give you the same CFT. So all of these are motivations for taking a fresh, different look at what conformal field theories are, which is kind of fulfilled by the conformal bootstrap. There's a clock there. Is the clock accurate over there? I just want to keep track of time. Yeah, thanks. So the conformal bootstrap philosophy is that instead of defining CFTs in some empirical ways, we are going to formulate some axioms that all CFTs should obey. So by starting from some physical principles that we know all the examples obey. So we can look at various CFTs and see that they obey some physical principles, and promote these principles to axioms that every CFT should satisfy, a very, very simple finite set of axioms. And then we can ask, can we prove general theorems starting from these axioms, or can we maybe classify all CFTs? This approach to CFTs was promoted originally by Polyakov in the 70s, and there was also important initial work by Ferrara, Gatto, and Grillo. And also some important work was done by Mazac and other authors, which I don't have space to write, but yeah, these are the people that started the conformal bootstrap. Without further ado, let me just write down what these principles are. Let me say CFT. So the first one, not surprisingly, is conformal symmetry. The second one is unitarity, and I'm going to explain in more detail what all these words mean. Unitarity is not completely essential to go through some of the steps of the recent bootstrap development, but we usually use it. So I would say sometimes can relax, even though the bulk of the bootstrap of the results in bootstrap literature actually uses unitarity, but there are also some works which do not rely on unitarity. And the third one is locality, which can definitely be relaxed. For example, in conformal defects or in this non-gravitational version of ADS CFT, we don't have a locality of the CFT, and still essentially the whole machinery of the conformal bootstrap goes through. Any questions so far? Yeah.
Do you want locality to have like a stress tensor?
Yeah, that's basically the definition of locality. You can motivate why locality means the existence of a stress tensor, but you can also think of it as a definition of what locality is. So you could, well, that looks like a very, very simple set of axioms. The number of axioms is smaller than the number of axioms for groups, for example. So perhaps CFTs are simpler than groups. Well, that's probably not true. But nevertheless, we have managed to, basically beginning in the 70s and especially in the last decade, people have managed to derive some very powerful consequences. So let me just give you a breakdown of some of the highlights that have resulted from a careful application of these axioms. So one of the important highlights is that we have managed to determine very precisely scaling dimension critical exponents of strongly interacting CFTs, in particular the three-dimensional Ising model. So I'm just going to write down precise of interacting CFTs. In fact, specifically for the three-dimensional Ising model, it is the most precise method at the moment. Second great consequence of these simple axioms has been a very good understanding of how exactly the bulk of ADS CFT emerges from the boundary theory. So let me just say emergence of ADS dual. And finally, people have managed to derive general theorems which apply in all CFTs and which are consequences of these axioms. I think Tom Hartman is going to speak more about such theorems in his lectures. So people have derived some general properties that all CFTs obeying these properties should satisfy. Examples are the average null energy condition and causality. Although causality has been understood, I think, independently in more general quantity theories, but I think the Bootstrap proof is worth understanding. It still taught us a lot about how causality emerges and is essentially a consequence of these three things. So that's what has been done. And before going into the technical details of the Bootstrap, I would like to maybe say what I think can still be done. So in a sense, what is the end game for the Bootstrap? Well, of course, I don't know, and probably what I'm going to write down is not going to turn out to be true, and maybe there are going to be even more exciting developments which we cannot even fathom at the moment. But nevertheless, let me just write a few things which I think we haven't seen any evidence against the fact that they can be done using the Bootstrap in the end. So it would be really nice to, in some sense, classify, at least in some limited sense, classify CFTs. Maybe assume a CFT has a certain global symmetry, the relevant operators transform in a particular way, and try to classify all CFTs with these properties. So for example, you can hope to prove that the only four-dimensional CFTs with n equals 4 supersymmetry are the n equals 4 super-Dalimils, which has not been proven. Or you could try to show that there are no interacting CFTs above 6 dimensions. And secondly, you can try to prove some more general theorems. Some examples that come in mind here would be the CFT version of the Noether theorem, which essentially says that if you have some conserved charge or some symmetry acting on the space of operators, then there must also be a local conserved current. We do not know any counterexamples of this statement, at least to my knowledge. Are there counterexamples, Chris or Bob? No? Yeah, but it will be. We certainly don't have a complete proof.
Isn't one example just theories without a stress tensor? They still have.
Okay, so you should if you want a local conserved current, you should also demand locality, I think. So you should assume there is a stress tensor to try to prove this theorem. Yeah, thanks for the comment. Or on a sort of more ADS CFTs setting, you could try to prove or disprove some recent claims in literature that there are no non-supersymmetric string theory compactifications. But I think one thing which would be very nice and which we still haven't done is to literally exactly solve some generic interacting CFT. So exactly solve a generic interacting CFT. You know what? I'm just going to say that solve the 3D Ising model. That's basically what I mean by a generic interacting CFT. But by generic, I mean that there are no additional strong symmetries. Like in 2 dimensions, 2D CFTs have the extra Virasoro symmetry. So in general, you certainly don't want to have a higher spin symmetry. Yeah. So yeah, just solve the 3D Ising model. I think. I'm not sure if it will be done. Hopefully it will be done. Maybe Bootstrap is going to be one of the ingredients. And I certainly hope that some of us in this room are going to make progress on some of these problems. Okay. So,
There are some counterexamples to another theorem.
uh-huh.
For example, if you consider 2, 3, U1 gauge fields and take the O2 rotations, the corresponding current is not gauge invariant.
Mm-hmm. So you mean the symmetry is the one which exchanges these two U1s?
Yeah.
Oh, okay. Okay, so a complex scalar.
There is autosymmetry and there's non-normalizable nota currents. It depends on normalizability you want to impose, but if it's a non-convex CFT, then you should relax the assumption.
I agree. I agree with you that. Okay, I'm not sure what is the additional assumption to kill your example, Mikola, but.
Well, it's not my example. I think Dan Kyle was discussing.
Yes, I've seen the talk. Yeah, but I still think that there could be some additional assumptions that under which this theorem is actually true. But I don't have a quick answer to that. Okay, any other questions or comments? Okay, so let's delve into the calculations.
Just a comment. I think the point of that counterexample is that if you have the U1 times U1 gauge symmetry, if you just look at the spectrum local, for P of local operators, then it would look as if there's autosymmetry. But of course, we understand that quantum field theory is not supposed to have the autosymmetry. But in that case, it probably requires looking beyond the set of local operators.
Mm-hmm. I see. Okay. Thanks. All right. So what I'm going to discuss now are the consequences of conformal symmetry and unitarity. Especially unitarity, because that's one of the things which confused me when I was learning about this subject initially. The rule of thumb when you want to understand the unitarity is to start in the Lorentzian signature. So we'll consider a quantum field theory, which is Poincare invariant, and actually conformal invariant, in a d-dimensional Minkowski space. And we quantize this theory on equal time slices. So these are the time slices in flat Minkowski space where x0 is the time. Now the basics of quantum field theory teaches us that there is an associated Hilbert space living on this spatial slice. And unitarity is just a statement that this is a Hilbert space, that there is a positive scalar product on it. Now, conformal symmetry means that well, the theory is invariant under certain geometric transformations. The transformations are translations, dilatations, special conformal transformations, and rotations and boosts. And I'm going to give these a subscript L to mean that these are the Lorentzian geometric transformations as opposed to the Euclidean ones, which will play a role soon. And okay, Okay. And Wigner has taught us that every time you have some set of symmetries acting, continuous symmetries connected to identity acting on your, well, on the physical system, these are represented by anti-Hermitian operators on the Hilbert space. So these are going to be promoted to anti-Hermitian operators. And usually people prefer to talk about them. People prefer to multiply them by I and call them Hermitian, but I think that's slightly confusing to me. So I prefer to think of them as anti-Hermitian, because then the finite transformations are generated by. So when G is the generator, then the finite transformations are generated by e to the lambda, where lambda is real, as opposed to imaginary. But that's just a matter of taste. You can put i's in the following formulas wherever you like. So this means that the Hilbert space is a representation of this of the Lie algebra, where the Lie algebra. Well, let me just write a few of the commutation relations. So the advantage of using anti-Hermitian is that there are no extra i's floating in the commutation relations. So it looks like this. It's a real Lie algebra. And the following, the remaining ones are familiar from Poincaré, so I'm not going to write them again. In particular, the Hamiltonian of the theory in this space is just minus I times P0L. So it's the translation in the zero direction, and these commutation relations are the same as in the real Lie algebra SO2, D. Now this means that the Hilbert space must be a unitary representation of this algebra. So as I said, all of these guys are realized as anti-Hermitian operators. And now that means that we should try to understand the irreducible unitary representations of this algebra, because the whole Hilbert space is going to decompose into these representations. So that's going to be the next step. I wanted to spend a little bit more time on this than on the following topics, just to illustrate how exactly unitarity. I mean, I should say this is one way of introducing unitarity. You could also start directly in the Euclidean signature and call it reflection positivity. But this is done in the notes by David and Slava. So I just wanted to use a different starting point to give you a different way of looking at the same thing. And yeah. Okay. Now, usually we face the same problem when trying to understand just general Poincaré unitary quantum field theories, and in that case, the answer is that the irreducible unitary representations correspond to particles, and they are labeled by mass squared and some spin quantum number. Now, in this case, mass squared is not a good label, because it doesn't commute with all the generators of the conformal algebra, and in particular, it can take any value in a given irrep of the conformal algebra. So that's not a good starting point. Instead, we will start with a generator which generates this O2 inside SO2, D, which is called the conformal Hamiltonian. So there is a specific generator which I'm going to call D, for reasons which will be clear very soon. And this generator is just P0 Lorentzian plus K0 Lorentzian divided by 2I. Now, this is because P0 and K0 are anti-Hermitian, now D is Hermitian, and it's also positive, which is not very hard to see. I mean, you can see that P0 divided by I is a positive operator, because It's basically the Hamiltonian. And K0 is related to P0 by similarity transformation. So you can also show that the sum of the two is positive. Now, this operator does not act geometrically on the Minkowski space because of the I, so that it will just not preserve the Lorentzian slice, but it acts geometrically in Euclidean signature, which is why we like Euclidean signature so much in CFTs. But so in a Lorentzian signature, if I forgot the I, the equal time slices under this transformation would look like hyperbole. So here, x goes up, x0 goes up, and this could be, for example, x1. When you go to the conformal compactification, well, when you draw the Penrose diagram of flat space, these hyperbole flatten out and become equal time slices. So that's why this operator is important, that it generates the translations in this Penrose diagram, which you should really think of as being the Lorentzian cylinder. So I can cover the Lorentzian cylinder with patches of these Minkowski spaces. Well, and the conformal Hamiltonian is precisely the time generator on the Lorentzian cylinder. Now, because the cylinder is just R times s to the d minus 1, and because s to the d minus 1 is the space, and it's a compact space, typically the eigenvalues of d are going to be discrete. So that's one nice fact about this conformal Hamiltonian. That as opposed to the mass squared, which is a continuous eigenvalue, this d is actually a discrete one. Now, okay. So what I drew here was the time slices of the d without the I, the Lorentzian version. But we can also just we can big rotate and go to the Euclidean signature. So let's define xd to be I times x0, like where x0 is the time, and let's draw the action in these coordinates. So now again we have the x0 equal to the 0 time slice, and now the d generator has two fixed points. One is at -1, and the other one is at 0, -1, and the other one is at 0 and 1. And the equal time slices of this one are just spheres, which become bigger and bigger and approach this time slice. And on the other hand, on the mirror picture at the bottom, these are of course not concentric spheres, but they approach the special case of a sphere, which is just the flat d minus 1 dimensional space. And now it is convenient to make a conformal transformation where you map this point to infinity and this point to the origin, where they just become concentric spheres. And the 0 time slice becomes the unit sphere. So the Hilbert space now lives on the unit sphere. And this is why radial quantization is useful. And we can also map this guy to the cylinder just by the usual procedure, which I'm sure most of you know, where the radial transformation is generated by d, and it is the same as the time translation in the Euclidean version of the cylinder. Now, what is the point of this whole discussion? Well, it's just that the hermiticity properties of the Euclidean generators are somehow more transparent for doing the representation theory. So now we'll have a set of Euclidean generators. We'll have a set of generators D without any L subscript, Pi, Ki, and Mij, where now I and J run from 1 to D. And they should be thought of as the generators acting in this flat space. They are linear combinations of the Lorentzian generators. I'm not going to show you the exact linear combinations. They can be relatively complicated. You can work it out as a homework problem. How are these generators expressed in terms of the Lorentzian generators? But importantly, they have very nice hermiticity properties. So I already said that D is a self-conjugate. P is a conjugate of K. And Mij is anti-Hermitian. So all of these hermiticity properties are always with respect to the same Hilbert space. It is the Hilbert space of the theory in flat space, which is the same as the Hilbert space here. So the reason why we are getting different hermiticity properties is that they are just different operators acting on the same Hilbert space. But the Hilbert space will always be the same. And well, the commutation relations look exactly the same as those of the Lorentzian ones. Except now there is a Kronecker delta, and they're like this. So this really means that we can think of this. We can think of P as a creation operator and K as an annihilation operator with respect to the number operator D, and Mij sort of goes along for the right, and it furthermore rotates us within a given subspace of a D eigenvalue. I think this is a review for all of you, so I won't go into the details, but basically it means that every representation can be built upon a primary operator, primary state, which is defined by Ki annihilating it. It has a fixed eigenvalue under D, which is called a scaling dimension, and it transforms in some irreducible unitary representation of the rotation group. So these Mij's now generate a group SOD. So small Mij are some representation matrices in a specific irrep of SOD. I mean, it's unitary because the generators are anti-Hermitian. Okay. And the rest of the irreducible representation can be obtained by acting with the creation operators, which are the P's. So the whole irrep of the conformal group of the original SO2, D. So a unitary irrep. I should say it is not a unitary irrep of the SO1. Sorry, I should say that the Euclidean generators form a real SO1, D plus 1 algebra. Of course, it's a different algebra because in doing the linear transformation from the Lorentzian ones to the Euclidean ones, you've introduced some i's. So in this way, you change the algebra. Okay, maybe I'm spending too much time on the basics, but anyway. These are not unitary irreps of the SO1, D plus 1. They are unitary irreps of SO2, D, and they are built from the primary by acting with the PIs. So in particular, they are all infinite dimensional. Sorry, Paul. Except for special cases, they are infinite dimensional representations. Okay, any questions about this? Yeah?
These are not the only unitary representations of the conformal group? So do the other ones make an appearance?
Well, these are the only unitary highest weight representations of the conformal group. I have to say, I don't know much about those which are not highest weight, but the fact that they are highest weight is implied by the fact that the Hamiltonian is positive. So because H is a positive operator, this is also a positive operator, and it's not hard to see that well, the scaling dimension must be bounded from below as a result of that. So all of such representations are well, those that I described here.
Is that why you chose P dot plus K dot rather than say minus?
Well, that's one reason. The other reason is that this generator is inside the cartan of SO2, D. It's the SO2 part, whereas the minus sign, it will be something off diagonal. It wouldn't be the SO2. I mean, you also want to start by diagonalizing the cartan. So.
Is there any importance of the Euclidean, I mean, unitary representation of Euclidean conformity, these complex dimensions?
Yes, there is, and I think well, they're going to make an important appearance in David Simons-Duffin's lectures. Okay, well,
You frame that the Hilbert space on the Minkowski space is same as the Hilbert space on this area.
the Hilbert space is defined with respect to a spatial slice. It's not. I mean, the Hilbert space does not depend on the signature, and the Hilbert space of a quantum field theory is a function of the spatial manifold that you quantize on. Right. So I pick some spatial manifold. Quantum field theory tells me, well, this is the Hilbert space, and then I can evolve inside this Hilbert space using various generators. I can pick the Lorentzian time translation or the Euclidean time translations, and they're going to give me different results, but they all happen in the same Hilbert space, which is just D1 associated to a given spatial manifold. Is this clear?
Still confusing because in the Minkowski space, this is a non-compact space.
Oh yeah, that's. Yeah, no, So this is a special property of conformal field theories, that you can make a conformal mapping between the flat r to the d minus 1 and the sphere s to d minus 1. So that you're right, that this will only be true in conformal field theories, that the Hilbert space on flat d minus 1 dimensional space is the same as the Hilbert space on the sphere. This is not true in general.
I guess you have the flat space you take is conformally invariant boundary conditions.
Yeah, exactly.
Same
Yeah.
as the sphere.
Thanks, yeah. I mean, you should really think of it as the Hilbert space on the Lorentzian cylinder. I mean, sorry, now I caught myself again and said Hilbert space on a Minkowski space, but yeah, you should think of it. You should always think of the conformal compactification, like the cylinder.
You mentioned unitarity was the existence of an inner product, which was positive definite. So, what is the inner product on the state you just constructed?
Well, all the inner products are already fixed by the hermiticity conditions. And yeah, I mean, the fact that different irreps are orthogonal to each other, and within each irrep you can always compute it by using the algebra and the hermiticity conditions. Okay. I mean, in the physical theory, the inner product is specified by the path integral. Okay, well, by the way, am I supposed to speak for an hour, or in the schedule it looked like an hour 15 minutes?
An hour 15.
Hour 15, and there's going to be a break then, and
Yeah.
Okay.
I mean, there's no break scheduled.
Okay, well, maybe we can take a break, but. All right, so now the Hilbert space decomposes into a direct sum over the primaries O in the set S, which will have the meaning of the spectrum of the representation labeled by delta O and some irrep of SOD, where this guy is a real number because of the hermiticity of D, and furthermore, delta must satisfy some bounds for depending on the so typically delta must be greater than some delta star, which depends on the representation. This is called the unitarity bound, and so it looks like we are done, because now we have the whole Hilbert space, we have the scalar product, but we are far from being done, because the whole structure really comes alive once you realize that the states that I just described are actually local operators. This is the essence of the state operator map, which I'm not going to give as much of an in-depth discussion as I would have liked to in the interest of time, but if you want to see explicitly how it works, there's a nice discussion in the first volume of Polchinski, chapter 2, which works it out in quite a lot of detail for the two-dimensional scalar field and some other two-dimensional CFTs. What I want to say is that to talk about it, we should really imagine that our CFT is defined by some sort of path integral. Now let's go to the Euclidean space, where we are quantizing on the S to D minus 1, and we can insert local operators at the origin, and by doing the path integral over the interior of the ball, we are going to create some state on the boundary. Now the point is that not only that we can map from these, so this gives us a map from operators to states, but this process can actually be reversed for some special states over here. So it is not true, as is often said, that every state in this Hilbert space gives you a local operator. That's a little bit imprecise, but it is true for these basis elements. If you take, for example, the primary or specific descendant, as long as you don't take infinite linear combinations with many different scaling dimensions, you can actually reverse this process, and you can start with some state, say this OA, and you can undo the path integral and find a nice local operator in here. Now the reason why it's a little bit imprecise to say that every state gives you a local operator is that there are obvious counterexamples. One such counterexample is that you can, which will play an important role quite soon, is that you can just consider some very non-local operator, say, well, a bunch of local operators inserted inside here, path integral evolve, that's going to give you some state psi, and you can try to evolve this state back to the origin. So you can try to replace this with some object in here, which is the supposed evolution backwards to the origin, but now this is not a real local operator, because, well, if you try to compute its correlation function with some operator at a radius smaller than this, than the radius of the furthest local operator, this just doesn't make sense. It gives you infinity. So it doesn't behave like a true local operator. So the right statement is that local operators form a dense basis for the whole Hilbert space. Local operators are dense in H, and it is precisely the basis selected for us by the representation theory of the conformal group. Okay. Any questions about this?
There's some assumptions that go into saying that every state or every operator gives you a corresponding state, like Levy theory, for example. There's not a state operator correspondence in the same way. The identity doesn't have a state. So what have you assumed about CFT for that?
What have I assumed about the CFT? Well, let's say I can always answer this question by saying, well, I'm just going to restrict the CFTs where this works. That's not really an answer. Well, I guess the problem in Liouville theory is that the vacuum itself is not normalizable, right? If I understand. Yeah, I guess. Yeah. Does anybody have a better answer?
Well, the identity operator is not normalizable in Liouville theory.
Yeah.
And you want to work with other normalizable operators. So I will say that the issue in Liouville theory has to do with what you want to call the space of local operators rather than the problem with state operator matching.
Yeah. So Yeah, so I guess, yeah.
What's wrong with saying that if you, in your counterexample, that if you evolve it back to the point, it means that you just shrink and collide all the operators inside the.
Well, I think this process of shrinking is can be a bit violent. I mean, you really need to shrink to 0. So it's not obvious that it works, and you actually need to work to show that it works for the eigenvectors of the dilatation operator.
Shrinking the whole configuration is just not the state to operator map. It's a thing you can do, but it's
You're not shrinking the point. I don't think that's what Nicola was referring to. You just wanted to take the state and shrink it, and you're asking what goes wrong when I try to shrink this psi. Yeah, it's just not a well-defined process. Yeah, you get. Yeah, I mean it's a proof by contradiction. It doesn't work because what you get here doesn't give you convergent it doesn't give you finite correlation functions. Okay. So now I finally can talk about the basic observables that the Bootstrap uses. And the basic observables are Euclidean correlation functions. These will be denoted like this. I take a bunch of local operators, typically primaries, at various positions in Minkowski space, and compute a correlation function. Now, what is this correlation function? Well, you can think of it in different ways. One way to think of it is that they are defined by some sort of path integral, that you can compute them even just formally, principle, by inserting the corresponding modifications of the path integral, which are these local operators, normalized by the partition function. That's one way to compute them, and the other way to think about them is as matrix elements in the Hilbert space that we have talked about. Where this operator in Euclidean space is defined, well, the operator at coordinates xd is defined like this. Sorry, plus hxd. So you're evolving using the Hamiltonian. But the important comment here is that such a matrix element only makes sense if all the xd's are ordered in the same way as is the ordering of these operators. So only while the path integral definition makes sense for any configuration, this definition using matrix elements only makes sense if the xd's are ordered in the same way as the operators. So one important underlying claim is that these matrix elements unlikely continue to these correlation functions, which sort of don't care about the ordering of operators. Very good. And sorry, I should say the reason why these guys only make sense in the ordering is that, I mean, because of this time evolution, you're going to encounter these differences. So say x1 to the d minus x2 to the d inside this matrix element, and while this operator is nice and this operator doesn't blow up, the operator with a plus sign would blow up. So that's why you need the proper ordering of Euclidean times. Now, as a result of conformal symmetry, these Euclidean correlation functions are quite tightly constrained. In particular, the one-point functions. From now on, I'm going to just will always be a primary operator, actually a primary scalar operator, meaning that the SOD representation is just the trivial one, the identity. So the one-point functions vanish unless O is the identity operator. The two-point functions are only non-zero when the operator have the same scaling dimension, and they look like this. And we can pick a basis in the space of primary operators in such a way that there is a delta, there's a Kronecker delta sitting here, that we only get a non-zero answer when they are literally the same primary operator. And finally, the three-point functions are also tightly constrained. Now, after we fix normalization like that, they contain an in principle undetermined number, and then I'm sure you either know or you can look up the exact dependence on x, y, and z. Over here, and because of unitarity, the basis that we've chosen also means that Fijk's are real numbers. Now, if you don't understand why, you can talk to me after the lecture, or you can look at in Chris's lectures from before. But I don't want to spend too much time on basic topics or basic claims. Okay. And now finally, the reason why our Hilbert space as a direct sum written over these representations really comes to life is because of the state operator. It's because of the OPE. The OPE gives us a multiplicative structure on this Hilbert space or space of operators. And that's really constraining to have this multiplicative structure. So what it is a statement that when we have a product of two operators, and let me for simplicity again restrict to primary scalar operators OI and OJ at two different positions. So we have a OI here and OJ here. Under certain circumstances, we can replace this product by an infinite sum over primary operators in our theory. So K is inside S, this spectrum, with some coefficients, Cij, there's a prefactor. I hope this is okay. Oh, sorry. Let me just set this to 0. Plus the descendants. And the form of the OPE is completely fixed by conformal invariance. So this prefactor is fixed by conformal invariance of the primary, and the way that the descendants of K, of OK, contribute is also fixed by conformal invariance. And to see how exactly this works, I again refer you to Chris's problem set or Chris's lectures from last year. And the reason why the OPE holds is because of the state operator map again. I mean, it's essentially what I was saying before, is that you can think of the product of OI and OJ as creating some state on the unit sphere. And while this state itself is not quite a local operator, I can always, because I have a complete basis for the Hilbert space, I can always expand this state in a complete basis of local operators. And that's exactly what this statement says, is that I can expand this. If you think of this as state, I can expand this state in a complete basis of states on the unit sphere consisting of local operators. Okay, any questions about the OPE?
So you started with 3 axioms, and now you introduce the state operator map, the path integral, and the OPE. Which one of these are part of the axiom, and which one follows from that?
Yeah, I didn't want to think of the initial axioms as the real axioms which I'm going to use in the end. These are more like the motivating physical principles, the precise axioms which I'm going to actually use. I'm going to state in 5 minutes. So I think that's one answer to that. But yeah, I mean, I'm not saying that if you start from those 3 principles, you can derive everything. There are still some extra, like usually in physics, things are not as sharp as in mathematics. And luckily, in the case of CFTs, we actually have sharp axioms, which are not the ones that were stated before, but the ones which I'm going to write down soon. Does this satisfy you?
Not really, but
Yeah. I shouldn't have asked that. Yeah. So the real statement of the most constraining principle of the conformal bootstrap is that this multiplicative structure is associative. So conformal bootstrap, to a large extent, is just a statement that this OPE is associative. I mean, it's just a statement that the product of 3 operators is equal to the product of 3 operators, where we can use the OPE either first like that, we get some infinite sum, and then we can do the OPE of that sum with this guy, or we can do it the other way, like that. And those 2 expansions must be equal as vectors in the Hilbert space or as local operators. So now one possible way to assert how to define what a CFT is, and I think she is not going to be happy about this completely, but I'll make some further comments, which maybe will make him a little bit happier, if not afterwards. So one way to define what is a CFT now is that we can completely abstract the basic players in the game, namely the scaling dimensions and the, one important thing which I forgot to say is that these Fijks are actually the same as thoseCijks. So theCijks can be computed by looking at the 3-point function, and you can do it just by computing by multiplying with OK over here and computing the 3-point function. So there are, another thing which I forgot to say, of course, is that now you can use the OPE to determine all the higher point correlation functions, right? When I take some endpoint function, like here, I can do the OPE consecutively, say O1, O2, that reduces me to an infinite sum over n-1 point functions, and I can recurse this process to get down to, say, 3-point functions, which I know how to compute. So this OPE determines for us all the correlation functions of local operators in our theory. So I can now define a CFT to be a collection of these local operators of O's, OI's, with the label and their labels delta I and rho I, together with the structure constants. Such that theCijk's are real, the delta i's satisfy unitarity bounds, and the OP is associative. Now this set of axioms is, well, this sort of axiom or definition is extremely constraining. It isn't. I'm not claiming that this is a complete set of axioms in a conformal field theory. There could be some extra things you need to add in, especially about the behavior of CFTs on other manifolds. Like typical case is in 2 dimensions where these axioms on their own would not imply modular invariance of the torus partition function. So you may need to throw that in, and it is not understood in general. Certainly in higher dimension CFTs, it's not understood in general what is the complete set of axioms that would guarantee a consistency of a CFT on a manifold of a general shape and topology. But it is believed that at least when you restrict to conformal field theories in flat space, this is to a very good degree a complete set of axioms that you need to find a consistent conformal field theory. That's a great question. Consistent basically means that it gives you sensible physics, be it physics in the Euclidean or Lorentzian signature. So, for example, one important property that the consistent field theories should have is causality in Lorentzian signature. That means that you cannot send signals faster than the speed of light. And this is not included in the axioms, but you can actually derive this property. You can derive this property of Lorentzian correlators starting from these axioms. So causality is an example, but yeah, I think it just means that we are one day if we manage to classify all CFTs just starting from these axioms, it doesn't mean that we are going to find one example of a solution and say, oh, this is really not a good CFT. I mean, yeah.
The consistency of putting a CFT on a general manifold just means that you can slice the open along any spatial slice, any circumfleet basis of states, and get the same Fourier function. But as far as that is concerned, it's not obvious why you need to care about putting on general manifolds in higher than 2 dimensions. On 2 dimensions, because you slice it open, you have a circle, and you have the same Fourier space as the local operators. And it's not very obvious why you need to want to impose that. But whatever you need to think about it. But if you don't include that, for example, you definitely cannot prove Noether's theorem, because as was mentioned earlier, the U1 times U1 gauge theory, and well, if you take this to be the axiom, you will conclude this O2 symmetry, and there will be no Noether theorem.
Mm-hmm. Okay, thanks. Yeah. As I say, even after preparing these lectures, I still can't claim to know everything about basics of CFTs. Okay. Well, I still have 3 minutes before the. Okay, more questions. That's a good way to fill up the last 3 minutes.
It's like related to what Joe was saying. So like when you say CFTs on a general manifold, what kind of general manifolds are you looking for? I mean, why are you looking for conformal invariance on a manifold that's already, like not even scale invariant potentially?
Mm-hmm. Yeah. So in a completely consistent CFT, you should certainly be able to place it on manifolds which do not have the conformal group as their group of isometries, or a group of symmetries. I mean, it is closely tied to the locality of the theory. That somehow, when I place it on flat space, I should be able to deform the flat space into maybe make a little bump in the flat space, and this is done by inserting a stress tensor there. So this would at least tell you how to, in principle, define the CFT on a curved space, which is some continuous smooth deformation of flat space. Yeah, but you may not want to impose this requirement. I mean, it may be that there are interesting structures which are CFTs in flat space, which somehow don't allow an extension to curved manifolds.
A strong notion of locality would demand that if you have a theory define some manifold, to be able to kind of cut off some piece of it along some collimatrix 1 surface and glue in another manifold. So by that way, we in principle be able to define this on any manifold, but then you have to ensure that it's actually consistent. So it's a very strong notion of locality to say that you can put a theory on a general manifold. But then there's also further ambiguity. If the manifold is not conformally flat, you can decide what we mean by putting safety on the manifold by deforming that by some higher dimensional operator coupled to the curvature of the manifold. So then even some theories that we think are nice can behave badly if you choose the wrong couplings.
Okay. It's great to have Xi in the audience. It's wonderful. Like he knows everything about this. Okay. Well, I think we should just break now, unless there are further questions about what we have said so far. Okay, Alex, did you have a question?
Why is it okay that you can assume that the Hilbert space is spanned by local operators? Is there a CFT where that wouldn't hold true?
It follows from Riesleiter here. Riesleiter here.
Oh, Ries, like R-I-E-S-E.
No, Riesleiter here. It's explaining what it's not.
Okay. And any more questions? Either for me or for Xi?
About the last point where consistency on general manifolds is a strong notion of locality, I can attest that Leonardo knows it too.
Yeah. No, I didn't mean to say that she is the only person in the audience that knows everything. That's not what I said. Okay. Well, let's take a break then.
I actually have a key question. So about locality, when we say we don't need locality or we can relax the assumption of locality, we still have the stress tensor, right? We should.
No, it makes.
Can we have theories in which we don't have the stress tensor? Because don't we need the stress tensor to define the conformal symmetry to begin with?